So I've got this idea of J, and J actually, well, it's impulse. But as it turns out, and we're going to talk this through, this idea of impulse is equal, at least in magnitude, to the idea of how much the momentum has changed by. And I'll put like a little bubble around that because I want to kind of work my way through this. J is impulse. Momentum 2 minus momentum 1 is how much momentum has changed by. So I want to start off with equation 1, and I'll just use this thing that I just talked about. J is equal to P2 minus P1. I'm putting those arrow hats on top of the vectors for now, and maybe later on, actually, you know what, maybe I'll stop using them right away. Equation 2 is going to be acceleration equals V2 minus V1 over delta t, so that's that rate of change of motion, acceleration. And I think I'd like to, maybe let's put a little divider here. I want to have another equation, equation 3, and we'll use Newton's second law, F equals ma. So we're actually using a couple of things that we're very familiar with, and this new thing, the change of momentum. Now, I know that F is equal to ma, Newton's second law, could be used with these guys up above. I actually could make a little note to myself, sub equation 2 into equation 3. And if I sub equation 2 into equation 3, I would end up getting F is equal to mass times V2 minus V1 over delta t. And of course, anytime I have a coefficient out front of a binomial, I'd like to multiply through. You know, we call that the old distributive property trick. Multiply that m through the binomial, and I end up getting F is equal to mv2 minus mv1 over delta t. Now, if I put a box around that, that's not my end point, but I do want to look up and just notice, see equation 1. And as soon as I do that, see P2 minus P1? MV2 is P2. MV1 is P1. So I've already got things coming along in the right direction. I'm going to make a little note up to here and say, okay, well, MV2 minus MV1, that's the same thing, or at least it's equivalent to talking about the impulse divided by delta t. And if I rearrange this one, I can get J all by itself, get the impulse all by itself. J is equal to force times delta t. So this J is equal to force times delta t that's in my little text box here that I haven't really acknowledged yet is the impulse. We're using the variable J for that. Notice that J is a vector, F is a vector, time, of course, not a vector. I'll put a box around it, and I'll say this is our formula for impulse. And I want to say that equivalently, but not the same thing, change in momentum, or delta P, is equal to P2 minus P1. Now, just as a sidebar, what I got over here, rate of change of momentum, really change of momentum divided by change in time. Rate of change of momentum being equal to force. This is how Newton actually thought of his own second law. So I know we always learn F equals ma, but this is the way he was thinking about it, was that there was the rate of change of momentum. Another little side thing here about this idea of impulse is that if I were to make a graph, and I were to graph the force that I apply to an object as a function of time, you might get a graph that looks something like this. You notice there's, we could break this up. I obviously had the force ramping up a little bit, and then it becomes constant as you push something along. We could break this graph up, and I can see that I could break it up into, this is a nice geometrically shaped graph with uniformly increasing force and then constant force, but I could break this up into a triangle and a rectangle, and then I'd have another big rectangle shape. The idea here is, though, that if I was going to calculate the area of that rectangle, it would be force times time. You see that? That height would be a unit of measurement of force, and the base would be a measurement of how much time has gone by. So when I calculate the area under a graph like this, just making that kind of a geometric connection, this tells us that the area under a force versus delta t graph is impulse. And I could also say would let us calculate change in momentum. So that's kind of a handy thing. That's a little bit of the quick theoretical background before we move on to the next stuff.